Good morning, Earth Science, and welcome back. Today we are getting to a chapter that's been long anticipated. We've been talking about it a lot. We're getting into weather, chapter 20 here. So we're going to talk about this thunderstorm on this picture here, but we're also going to talk about air fronts. We're going to talk about warm fronts versus cold fronts. We're going to talk about hurricanes. We're going to talk about tornadoes inside of this one. So we're going to talk about all these things that you're used to seeing on the news, and we're going to kind of break down what that means when we say that we have a cold front moving into the area and what you should expect the weather to do after you kind of hear that. So the first thing we need to talk about is air masses and weather. Weather itself affects our daily lives. It's something that we talk about quite a lot, especially as you get into your adult lives. You will say, "How's the weather?" more than you would care to admit. But it depends. It kind of, as it affects our lives, we make decisions. Do we get an umbrella for the day? Do we wear sunblock? So we like to know ahead of time what the weather's going to do. And so we have a whole field of earth science meteorology to studying these processes and making the ability to predict weather more possible. And we're still getting better at it, and we're not always right 100% of the time, but we will kind of learn how we make these predictions based on what we're seeing in global wind patterns and air masses and etc. So a meteorologist has a lot of jobs. He can be as simple as making a weather forecast all the way to studying how tornadoes develop and how massive a hurricane is going to be before it hits coast. So a lot of this is studying air masses. So we're going to jump into air masses. And air masses are a large body of air in the lower troposphere that has the similar characteristics throughout. So what you would expect is if in a air mass, in a chunk of air, it's all going to have about the same humidity level and all about the same temperature level. So if it's going to be 60 degrees, it's probably going to be 60 degrees for that whole air mass. So these guys can be really, really big or smaller, just depends on how long they're able to form and what the conditions are on the surface and that uneven heating of the Earth's surface. So we can go from several thousand kilometers in diameter and several kilometers high. At any one point in time, we can have, if we have really big air masses at the point in time, we can have 2 or 3 air masses can cover all of the continental United States. Or it can be as many as 6 to 8. But throughout that mass, your temperature and your humidity are going to be pretty close from one end to the other, from the western end to the eastern end, from the northern end to the southern end of that air mass. So where these guys come from matters, and it kind of determines what properties they have. So the temperature and the humidity of an air mass depends on where it originates, not where it moves to. So if you're in the polar regions and you're getting an air mass that's forming there, this lack of sunlight causes the ground to be very cold. If it stays there for a long time, that whole chunk of air is going to get bigger and bigger, and it's going to stay that same coldness, same amount of humidity there. And then if it moves into a different area, it's going to carry that coldness and that lack of humidity with it. On the opposite, if you're in the tropics and you're along the equator and you're constantly getting sunlight and you're constantly getting enough energy to evaporate water into the atmosphere, that air mass becomes hot and humid. Air masses that originate over land are going to tend to be drier because there's not as much liquid there versus the ones that form over oceans. If you're an air mass and you're forming over the ocean, you're going to pick up a lot of water inside of you. And as you move onto the continents, you'll probably lose that in the form of rain. So something that we've alluded to is that air masses are not stagnant. They don't stay in one spot forever. They end up at one point in time moving from one area to another. And as it does, it takes that temperature and that humidity from where it originated and moves into the new area. So like in the United States here on this map, we're in the Chicago area and it's cool and crisp in the fall. We have this colder air from Canada moving down into the United States here, this continental polar. We're going to talk about these different air masses, but this cold air bringing this temperature down. Kind of on the flip side, in the summer, where we have this warm air from the Gulf of Mexico, this moves up, and Chicago is now muggy and warm. It has a lot of liquid in it, it's very humid, and it's very warm during the summertime. So as these guys move around, they do change. As the polar masses move south, they heat up and they turn into more of those tropical fronts. And as those tropical fronts move north, they turn colder and turn into cold air fronts. So these guys are constantly changing and kind of battling, doing kind of like a push and pull, almost like a tug of war. There are several different types of air masses. We're going to talk about a couple of the major ones. And we classify air masses based on where they originate, where they started out before they came into the area. And the first, we're going to start in the north and work our way south. The first is the continental Arctic air mass. And it originates in the extreme Arctic areas where the air is really, really cold. As they move south, they can warm up a little bit, but they're still going to bring a lot of cooler temperatures than, even in the summertime, than what is in that normal for that area. So if they're passing over snow-covered ground, they are staying even colder longer, so they're able to move further down before they warm up. With these, they're very dry fronts, and the very reason that they're dry is because the air is so cold where they originate, they're not able to evaporate any water and carry that with them. So versus our tropical areas where they have a lot of heat to evaporate water, the polar ones don't. They don't have a lot of energy to do that kind of stuff. So they just get cold and they stay very dry. Right in up here in the northern hemisphere, up in Idaho, when we get that really, really long cold spell in January, that's from that continental Arctic air moving down into this region and kind of getting stuck here for a couple weeks. Our next one, kind of moving down, is the continental polar air masses. And these air masses are originating over inland regions of Alaska and Canada. If you're not looking at the United States, it would be more like Russia or Norway or Sweden. But these guys are slightly warmer than continental air masses, and they have a little bit of difference in humidity. But these guys are still, because they're forming over continents, going to be pretty dry. So when we get sunny, cold days in parts of the United States, this is caused by this continental polar, which doesn't have a lot of liquid, so there's not a lot of clouds, coming down and chilling the area. It can cause precipitation when it comes over areas like the Great Lakes. In the United States especially, looking at this map here, you can see that the Great Lakes are kind of the only inland water that's big enough to denote on this map. So any mass that's big enough to be on the map is going to be big enough to cause rain. So we get some snow downhill from those, kind of downwind, and this snow is a heavy snow, and it's called, when we get it, it's called the lake effect snow, because the snow is really wet and really heavy, and usually melts off pretty quick, because this air is kind of warmer than that continental Arctic. All right, kind of moving to the outsides now, we're going to talk about maritime polar, and all of these get a two-letter abbreviation. Continental polar was CP, continental Arctic was CA, maritime polar is MP. You'll notice that the where it originates is lowercase, and the temperature that it is uppercase. So this one's marine polar, maritime polar, so it's MP, and the P is capital. And this is originating over the oceans in these more northern regions, further away from the equator. These, because they're over the oceans, are both cold and damp, so they're going to have some moisture in them. Because of this moisture and this kind of insulating effect that water has on temperature, maritime polar air is not usually as cold as continental polar because of the contrast between the land, which is colder in the winters, and the oceans, which are warmer because they have those ocean currents and they hold on to that sunlight longer. If this maritime polar air cools to its dew point, you get fog, you get clouds, or you get precipitation. So areas that are going to have a lot of this on this map looking at the United States are going to be areas like Alaska, areas like Seattle or Washington. All of the Washington coast and Oregon coast are on this kind of map here where we get this a lot of rain, a lot of fog, a lot of moisture as this maritime polar is bringing in this cold, moist air. On the East Coast, when it comes off the Atlantic, we can get heavy snowstorms called nor'easters. These are the really, really famous ones where we get like 6 feet of snow overnight, like in New York. They're not as common, but they do happen. Every year we get nor'easters. They're usually not that much snow. They're like 2 feet, but still pretty significant. Good enough to get a snow day. All right, moving south, but staying in the wet area, we're going to talk about maritime tropical, or MT. So these is air masses that are originating over a warm tropical ocean. And because of this, it is getting both warmth and moisture. In the summer, we get this maritime tropical air coming from the Bahamas and the Gulf of Mexico, moving clockwise. It's coming up and around the high pressure area of the Atlantic Ocean. And this brings a lot of heat and humidity, especially to this Midwestern area over here of the United States. It also brings a lot of heat to Baja California, Latin America, parts of California as well get some of this. With this very, very hot, very, very wet air, remember that those are the two main ingredients for thunderstorms. So when we get this hot, moist air moving into these regions, usually we get a lot of thunderstorms happening as well. And even up here in the northern part of United States, we get these summer storms as well, as this maritime tropical is moving in and creating this perfect conditions for these thunderstorms to happen. The last of the air masses that we're going to talk about are the continental tropic, and these are C with the T. And in the United States, these are the kind of smallest amount of air masses that are being produced. In other parts of the world, such as South America or Africa or even parts of Asia, these areas are much more significant, and there's a lot more of this hot very dry air being produced. So, continental tropic is over deserts. It's hot and dry. They can start as maritime, but as they move into the mountains here, that water evaporates even further into the atmosphere and kind of becomes unusable. These can reach temperatures of above 100 degrees, and they don't bring clouds and they don't bring thunderstorms because they're dry air masses. They don't contain liquid. If this pushes into an area where agriculture is an important staple and stays for an extended period of time, this can often cause really, really serious damage to crops. They don't like being that hot for that long. So when we get these kind of droughts and these things, it's because of this continental tropical air kind of blowing into an area and making sure that there's no available water for rain or precipitation or even dew. So when you get your really, really hot days, it's probably because you're getting some of this continental tropical moving in for a little while, and then eventually it will usually come to a head as different thunderstorms move into the areas. That maritime tropical comes in and pushes it out. All right, so now we need to talk and kind of shift and change gears here and talk about air fronts and the lows that they cause. So we live in the mid-latitudes. Anywhere that you're in the mid-latitudes across the world, the weather changes almost daily. So air masses don't like to mix with each other. When they do, there's this exchange of heat, and usually that's an exchange of weather. So the boundary between these two, in this picture here, it's this kind of blue line, is what we call a front. And these can be really, really big. They can be 100 miles wide, 3 miles high, and 1,000 miles long. So they can take up a large portion of a state, of a chunk of land, of a whole area. And they're most common where we have this southward moving polar air mass mixing with tropical moving air that's moving north. So as these two come together, and however they're interacting, we will get a front. And there are several different types of fronts, and we will talk about those. So when you hear that there's a hot front moving in, you know what that is versus a cold front. So what's happening at this front? At the front, the air masses have either different temperature, different humidity, or they have both different temperature and different humidity. The less dense air mass is going to rise over the denser one. So usually the less dense one is going to be the warmer, wetter one, kind of like what we talked about last chapter. This ends up causing a kind of wedge shape as these two comes together, where the less dense, warm air rises over the cold, denser air. As this happens, this warm air usually cools down, and so fronts usually bring precipitation, as this moist air is rising up, forming clouds, and then falling back as some kind of liquid. The first kind of front we're going to talk about is a cold front. It is denoted with these kind of symbols up here, where it is these blue triangles. For a warm front, it'll be that redder semicircles, and then we'll talk about stationary and included coming up. But we define fronts based on which front is moving into the area, which one is advancing into the area. So in a cold front, the cold air is moving into an area that already has warm air. As it does this, it pushes this warm air up, and it continues to try to move forward, but because it's getting friction on the ground, it's starting to slow down a little bit. So an example of this happens when we have that continental polar displacing humid maritime tropical air in the summer. And because of this, we get thunderstorms that are forming along the front as this warm, moist air is trying to rise, trying to get out of the way of this cold air. And this cold air is constantly pushing it higher and higher. So usually these guys, because they have a really steep slope, they happen really fast. These kind of fronts do. The kind of precipitation that we will get usually only lasts a day or two, not very long. The second type here we're going to talk about are warm fronts, and this is where warm air is moving into an area and displacing cold air. So as it moves into the area, it doesn't want to mix with that cold air, so it starts to rise to the top of it. It has a much less slope, as you can see in this picture here. It's kind of like this kind of nicer line here. If you were going to be sledding down this hill, you would like this hill a lot more than the previous one where it was really, really steep. So the first signs that we're getting a warm front are those high cirrus clouds, those really stringy looking ones, and then those ones are going to be replaced by those cirrostratus ones. As these move up, this is because this clouds and this water is moving up higher into the atmosphere. As it moves higher in the atmosphere, it starts to cool off, and these clouds start to form. With these guys, because the slope is much less steep, and because it is coming, it goes over the top and hangs around a lot longer, we get precipitation for a lot longer with this kind of front. Usually 3 to 4 up to a week days of precipitation. And the warm front symbol here is this kind of red line with these semicircles. You can look at a map in black and white and you know that the semicircles mean warm and the triangles mean cold, but it does help when you have a kind of red and blue denotation as well. Our next ones here are occluded fronts. And these are happening when we have a cold air catching up to a warm front. So something to note about cold fronts is usually they're coming from high pressure areas, so they're moving really, really fast. Just about it is twice as fast as a warm front can move. So as this cold front catches up to a warm front, we get what's called an occluded front. The warm air is caught between two colder air masses. It starts to rise up. As it rises, it starts to cool, often causing a lot of cloudiness and precipitation. For this one, we use the purple weather symbol here, where it is a purple half circle and a purple triangle as we're meshing that cold and hot air together. So it gets that purple denotation. You'll also note that they're on the same side of the line. That's going to be important when we talk about our next one, which is stationary fronts. All right, stationary fronts. These are when a front is not moving forward, it is now stationary. The warm air is trying to rise over the denser cold air. As it does this, we get clouds, we get precipitation. This one, we get lots and lots of rain. And if this front stays stationary for too long, we can get flooding. So these ones are kind of something to look for, especially in our dry regions that are really, really susceptible to flash flooding. These guys are a little bit more, you'll get flash flood warnings and flash flood watches to look out for these kind of things. This guy's weather symbol is the red half circle with the alternating blue triangle. This one's not purple, and you notice that they're on the other side of the line from each other. So that's how you can tell a stationary front from an occluded front. All right, we're going to look at here a low pressure, and this happens usually in mid latitudes, a low pressure system. And you can see that these start to get kind of complicated as we start to look at them. You can see we have a warm front and a cold front. Kind of this cold front is trying to catch up to the warm front, and the warm front is trying to get away from it. So as this cold air moves in, it meets this kind of tropical air here. It can grow into a really big storm system as these two are trying to catch up and get away from each other. So these guys are trying to mesh together. It takes about 12 to 14 hours for this to become occluded, where the cold air actually catches up to the warm air. And once we get this happen, then we get high winds and we get heavy rains. The first time we kind of like started to match these systems where it was the cold air and the hot air coming together was during World War II. So we have kind of limited knowledge about this still. We're still learning more every year about weather on Earth and how these systems form and what to expect as far as rain and how much rain and how hot and how heavy. So we are still getting some information here. But a lot of this is due to upper airflow. As we get these low pressure systems forming, the upper air is still going kind of through the jet stream there. So the high pressure from the jet stream is kind of spiraling down into the low pressure area around the Earth. Remember that the Earth is going to warm up faster, especially in the summer. And this hot air is going to try to escape back up to the surface. So as we get this kind of flowing through, we get what are called ridges and troughs, depending on the air pressure. And troughs, think of troughs as like traffic jams. Whereas these upper level winds kind of approach, the air gets kind of jammed together. Much is the same thing as like when you're going around a corner and all the cars have to slow down, all the air has to slow down too. And as it does, it builds up in kind of a traffic jam. Some of this air stuck in this traffic jam is going to sink to the Earth's surface. This sinking air increases the pressure at the surface, which means if you have more pressure, you have more wind. So you will get more surface winds when you have one of these systems going on. On the other hand, the air that is coming from the high pressure is going to kind of move into what we call a surface low. So in this picture here, this cold air is moving into this low here. The low pressure is trying to spiral back out and kind of go back up to that upper atmosphere. Remember that low pressure means hot, humid air. If more air is rising, this surface low gets even more low. And remember that whenever we have this difference in pressure, that high pressure wants to flow into that low pressure. The more pressure that we have, the more difference that it has, the faster the winds will be. So, however sharp the trough is up above in that kind of jet stream determines how much air is sinking down in here, creating this high pressure on one end and the low pressure on the other, causing these really strong winds. So some weather that we see whenever we get these pressure systems kind of depends on where this low pressure area is moving in relation to you. If you're in the northern hemisphere and a low passes to the north of you, you'll have a warm front move over you and then be followed by a cold front after that. If it's to the south of you, if this pressure system moves south of you, you won't get any fronts moving over you. You kind of stay the same, but you will get either steady snow or rain depending on what time of year you're at. So let's talk about when it moves to the north of you, because I think that's the more complicated part of this. And if it's it's heading east, so it starts in the west and going east, and it's moving to the north of you, what's going to happen is you're going to have the warm front pass over you. As it does, the temperatures are going to warm, the winds will start to shift, and the skies will clear. If you're towards the center of the low, you may get some rain, but you're going to start to get more rain as the cold front approaches. As that warm front moves out of the area and that cold front kind of moves in, it is going to have some scattered showers. You're going to have possible thunderstorms. You're going to get snow if you're there. As that cold front kind of moves through you and past you, the temperature is going to drop, the winds will shift again, and the skies will clear. This is because all that precipitation is only happening at the front where that warm and that cold air are meeting. So once you're inside of the cold front and that cold front starts to move past you, you're going to stop getting any kind of rain or precipitation with that front system. So, and then next we'll jump into talking about thunderstorms and tornadoes. Okay, now we're getting into the exciting parts of weather here, when we get these very extreme events like thunderstorms and tornadoes that start to occur. So, storms come, all shapes and sizes. We get these low pressure systems and we get hurricanes. These kind of weather processes can be hundreds of miles across, or it can get very localized where only one area we get scattered shower storms where they're only happening in certain areas and they're much smaller in comparison. So thunderstorms is any kind of lightning, thunder, and rain that's happening. Sometimes, depending on wind speed, we'll get hail forming in there. But these can be only a few miles wide, or they can be really, really large. So it just depends on what's going on in that system and what kind of is fueling this storm. So how big the storm is in area doesn't determine how destructive it is. A really, really small storm can be really, really destructive, and a really, really large storm can be very, very mild. So thunderstorms most commonly form from cumulonimbus clouds in warm, moist, unstable air. So with this warm and moist air, they bring torrential rain. They have the potential to bring tornadoes. They most often appear in the afternoon because we have this surface warming, making this hot air kind of starting to go up. As this air is moving, it becomes unstable. It's changing its kind of dynamics. So we get cumulonimbus as this hot, warm air is forced to move up. As it does, it forms this really big cloud here that's moving in this direction. This one is forming not over a mountain range, but there is a cold front here, and this warm air is being pushed up. You can see the mixing there of the purple, where this cool air coming down. And you can see that in this cool area, we have precipitation. On this other area, we have very dry air. So each one of these like kind of arrows here is what we call a convection cell. And so there can be one, like in this example, or there could be many of these stacked next to each other. So there'd be one here, one next to it, one further on, so on and so forth. Each one of these cells lasts about an hour or less, depending on how fast and how much rain's going on. So what happens is these cells will recycle. We'll have a cell form here, and then as this one starts to die out, another one will start up in the same spot or very similarly to it, and we'll get another convection cell going on there. We get these thunderstorms like this one where it's forming on a front, and they are called frontal thunderstorms. When we get these guys forming, we get what are called squall lines, and these are lines of thunderstorms that are appearing in front of a front. So we have this cold water coming in and this warm air, cold air coming in and this warm air kind of meeting it. We get strong winds as we have this high and low pressure. We get rain falling in the cold part of it back here because remember this warm air is moist. It's going up as it cools and goes back down. It forms rain. So this cold air is moving in here. If this is moving really slowly, we're getting a lot of rain in one area because this constant bringing in of warm, moist air here is going to constantly fuel this precipitation in the back. So if this happens over a long period of time and this storm doesn't break, we can get over precipitation and start to get flooding. With thunderstorms, sometimes we get something like this called a supercell. We get a very large, it's a single-celled thunderstorm. It has very strong updrafts, meaning there's lots of low pressure air moving up in it. As this air moves up in it, it starts to spin, and as it spins, it develops a tornado. So these supercell tornadoes, they have the highest winds, they have very damaging hail because remember, strong wind means more hail, and they also produce very, very destructive tornadoes. With thunderstorms, we usually see lightning. And lightning is a discharge of electricity from a thundercloud to the ground, thundercloud to another cloud, or thundercloud to another spot within the storm. All thunderstorms create lightning. It's kind of in the name of it there. But we also get lightning from clouds of snowstorms. Dust storms can have lightning, and volcanic eruptions, such as this picture here, can also have lightning, as we have these charged particles that create electricity. We're still kind of figuring out how lightning in nature works, but the theory is, as those condensation nuclei that water is forming on bump into each other, they become statically charged. Much the same as when you take a balloon and you rub it on your hair or a cloth and then it kind of sticks to everything. That same kind of thing is going on. Or like when you rub your feet on the floor and then you touch something metal and you get that static shock. We think it's similar to that process, but on a much larger scale. So as these electrical charges are moving around, they produce a spark. Uh, Lightning heats the air, which expands very, very quickly and explosively. This expansion of air causes the sound of thunder. Because the lightning is moving much faster, we see the lightning way before we hear it. Lightning is very, very, very hot, up to 45,000 degrees Fahrenheit. And because lightning is electrical, it is going to flow best in materials that conduct electricity, such as metal, water, and wet ground. And it's going to want to strike the highest of these. So if there's a tree that's full of water, it's going to want to hit it, or a metal pole, or you out there on the golf course. Electricity can't flow through rubber, and there's some other things, but staying in your car during a thunderstorm is usually fairly safe. But as you can see here, that these differences of charges here, this negative wants to reach the positive, this positive here wants to reach the negative, this negative in one cloud wants to strike out at the positive in another one. So we're getting this electric, discharge. We're trying to stabilize these very, very negative areas with these very, very positive ones. In addition to lightning, sometimes thunderstorms have tornadoes. And this is this violently rotating column of air that usually touches the ground. Not all tornadoes touch the ground, but most of them do. These guys can be dangerous because they cause property damage, they can cause injury, and they can cause loss of life in extreme cases. Due to their very destructive and very unpredictable nature, they don't always move in straight lines. Tornadoes are really hard to study. There's a whole group of people who will chase down tornadoes and try to launch drones into them and kind of get some atmospheric readings on those kind of what's going on in there. So to create a tornado, a thunderstorm must have that rotating updraft where it kind of makes a circle and spirals up. And this is called a mesocyclone. It starts way up high in the clouds and then will descend down till it touches the ground. So tornadoes usually form at the back end of their parent thunderstorm. They then travel in the same direction as that thunderstorm. Inside of there, they can move in any direction and are very erratic. They're most common in this red area here called Tornado Alley, and it's because it has these three air masses that are contributing to this. It has the cool, dry air coming from Idaho and Montana and Wyoming, mixing with the moist air from the Gulf of Mexico, and the warm, dry air from the Arizona area. And New Mexico area. As all of these come together in Tornado Alley, they start to form these mesocyclones, and that's kind of the ideal condition for them. And that's why we get them in this area of the country. So predicting tornadoes. We can use radar to get a kind of clue as to when a tornado is going to happen. When we have thunderstorms and we see this hook shape right here, usually that means that we're going to get a tornado. As this tornado touches down, then we actually can see where this thing is, and then using Doppler radar, which is this picture here, we can track whether that part is moving, where it is moving in direction to our radar receiver. So while this is still better than before, it still only gives about 20 minutes of warning for when you see the tornado on the Doppler here and when people in their homes get the warning for it. With these, we issue storm and tornado watches. So we issue watches and warnings to give people time. A severe thunderstorm is one that gets wind gusts of at least 80 kilometers per hour, hail that is at least 2 centimeters in diameter, or it has a funnel cloud / tornado. If we get conditions that are serious enough, they issue a tornado watch. What a tornado watch means is that there's a potential for a tornado to be in your area. So people will go out and look and kind of scan the horizon and see if they can see a tornado. Once we see one and we know which direction it's moving, we issue a tornado warning. And this is you need to get into the basement or somewhere away from in the middle of the house, at the bottom of the house, and you need to shelter in place until this tornado passes over you. This picture above me is a bank of tornado sirens. When those go off, that means that there's a tornado warning and that you need to, as a resident of an area that has these, get into cover. All right, our next section here is on hurricanes and winter storms. Hurricanes are a large rotating storm, like the picture here, of tropical origin that has sustained winds of at least 119 kilometers per hour. The air pressure at the center of the hurricane here is very low. We call that the eye of the storm. And hurricanes get their energy from the heat of the surface ocean water. So they have different names based on where they form. If a hurricane forms on the Pacific, it's called a typhoon. If it forms on the Atlantic, it's called a hurricane. Hurricanes have this spiral structure. And at the outer edge here, the winds and the rain are comparatively mild. As you get closer to the eye of the storm there, the winds and rains get heavier, they get more wild, and they are strongest here right around the eye. As this warm air is rising up, it forms large thunderstorms, but inside of the eye, the winds are very mild and there is no rain. And we'll talk about why in just a second. As they form, we have to get a lot of hot, moist air forming kind of up from the water here. So what gives the hurricanes their power is this water that is evaporating from the ocean that is condensing into these storm clouds. Remember, condensing is a heating process, giving this kind of system power here. So if this humid air continues to replace it and starts to spin, we get this hurricane forming. You notice that the descending air in the middle in here is cold. Remember that cold air typically is less moist than warm air. So that's why the eye of the storm has no rain, because we have this cold air that's very dry kind of blowing into the middle there. The spin of a hurricane, it has to start spinning to develop into a hurricane, so it has to rotate. Because of the Coriolis effect, you can tell when you're looking down at space whether your hurricane is in the northern hemisphere or the southern hemisphere. In the northern hemisphere, these guys are going to go counterclockwise. In the southern hemisphere, they're going to go clockwise. So, and then near the equator, we don't have very much Coriolis effect because they're not getting deflected really strongly either north or south. So we don't have hurricanes around the equator usually. When we classify hurricanes, we base them and classify them based on their strongest wind. So a tropical depression is one that has winds of up to 61 kilometers per hour. And then a tropical storm, which is what's going on in this video, this kind of GIF here, is when winds are between 61 and 119 kilometers per hour. And then a hurricane is anything above that 119 kilometers threshold. Hurricane season in the United States starts in late May, early June, and runs through November. And as these hurricanes in the Atlantic, they're going to move initially west or northwest and hit the coastline on the east coast of the United States. The effects of hurricanes, as they come over land, they lose that ability to pull that hot water up. So they lose what's powering them. So they start to weaken when they go over land. But they can already have a lot of power and cause a lot of damage just from coming in off the ocean. So the damage can be from wind, it can be from inland flooding, or it can be from what's happening here, which is a storm surge, a very large wave of water. This is caused by the high winds in the eye wall. Remember that most waves are caused by winds. Really, really strong winds are going to make really, really strong waves. These big waves can swamp low-lying coastal areas and can be really devastating. In 1900, there was a storm surge in Galveston, Texas, and it killed nearly aroundish 6,000 people. But you can see here that on this picture, this is the normal high tide down here. And then this storm tide and this storm surge was an additional 15 feet above high tide. So a lot of these coastal areas are not that much higher than sea level. So when we get this extra 15 feet of water, it is pretty devastating. But with a storm surge, if you see this, like the ocean go out really far and then you see a big wave coming, that's what's happening. And usually by that time it's too late because these things move pretty quick. Like tornadoes, we have hurricane watches and hurricane warnings. We track hurricanes by satellite. They're really big, so as long as they form out over the ocean, we have lots of, well, we have more time than tornadoes. I wouldn't say a lot of time. When a hurricane is 24 to 36 hours away, they issue a hurricane watch. And when it's within 24 hours, it's a hurricane warning. As you can see here, this hurricane is expected to travel on this white line, but they have blocked out these big red spots here. That's because when this hurricane hits land, we don't really, we kind of have an idea of where it's going to go, but like tornadoes, they are slightly erratic. So they can change once they hit certain landforms. They can change direction and they could go anywhere inside of this red line. So that's why this watch area and this warning area is this whole swatch here. When we classify hurricanes, we do it based on wind speed. And so this one here is in, I believe, miles per hour. And we use what's called the Saffir-Simpson scale. So at a Category 1 earthquake with winds of 75 to 95 miles per hour, we get down trees and roof damage. As we move to category 2, which is 96 to 110, we get home damage, we get large power loss. As we move to category 3, the winds are now moving at 111 to 129 miles per hour. We get major home damage and no power for weeks as we like rip apart whole infrastructure. As we go to category 4, we get devastating damage. We get homes destroyed because the winds are at now 130 to 156. And anything bigger than that is a category 5, and it's 157 miles plus. And this area is now uninhabitable for weeks or months after this hurricane goes through. It is extra devastating, and it does a ton of damage. A little less severe, we're going to talk about winter storms. These are from mid-latitude low pressure systems, like we talked about earlier in this chapter. They produce heavy snow, they produce ice, they produce rain. And often, if you're in an area that has a winter storm going on, you have heavy snow, ice, and rain. You have all three types of precipitation coming down. All right, blizzards. Blizzards are a winter storm, and they have to be considered a blizzard, you have to have high winds, low temperatures, and falling or blowing snow. So your winds must be larger than 56 kilometers per hour. Your temperature must be -7 degrees or lower, so way below freezing. And then the falling and or blowing snow must reduce visibility. So in this picture here where you can't see very far in the background, that visibility is reduced. In the United States, most of our blizzards occur in the Great Plains, but we do get some down in Texas. We don't get a lot of blizzards up here in the Pacific Northwest because we don't get a lot of that blowing snow that's going on there with the high winds. Most of the time we just get heavy snowfall. We can get them, they're just less frequent. Nor'easters produce extremely heavy snow. We've talked about them before. It happens when we get this low pressure system off of the North Atlantic Ocean. The temperatures aren't cold enough to make a blizzard, but if they do, they are really, really devastating. We did have a blizzard in 1888 in New York, and it killed 400 people. But the nor'easters can have a lot of snow, up to 50 to 100 centimeters tall. And this is a nor'easter here. This gal is kind of standing underneath this snowfall here that they've shoveled out. They get really, really a lot of snow really, really quickly in a nor'easter. All right, the last part of this chapter is about forecasting weather. As a global community, we're interested in forecasting weather. We're interested in following highs and lows and air fronts as they move around the globe and how this is going to affect our local weather. In order to get a full picture, we have to collect data from a lot of sources because we're talking about a lot of different factors. So we use a lot of tools. One of the tools we use are satellites, and they help provide weather information on every spot of the globe. This includes areas that there's not a lot of people living, or maybe not a lot of weather equipment out in, deep parts of Alaska and Canada. We use two different types of satellite images for weather. We use visible images and infrared. In visible images here, we get a black and white picture of the Earth. The white color shows sunlight that is reflected off of clouds or snow. The brighter the white, the thicker the clouds. So in this picture here, you can see that there's some thick clouds over here, and then there's some snow up in here. Gray colors are usually land, so this is all land here, and then black is water. So in here, you can see the Great Lakes are black. You can see that the oceans are black. There's clouds over the Pacific over here. By tracking the movement of these white patches, we can see, how big storms are getting. We can see how thick the clouds are. And we can, with those, kind of associate rain and hurricanes and tornadoes. The only problem with visible images is because they're based off of sunlight reflection, we can't get them at night. So they're only available during the day. So they are a little limited that way. Our next one is infrared satellite imagery. So we're using temperature rather than light to take images. These can be taken both during the day and at night because they're not requiring on sunlight, they're requiring on temperature. The bright areas represent cold temperatures. Usually this is the high top of clouds. So in this picture here, you can see that there are clouds in Montana, over Wyoming, kind of in this area over the East Coast-ish. The darker areas are warmer and represent lower clouds or a lack of clouds. You can see once again, the oceans are fairly dark here because they have a lack of clouds and they are warmer. Because temperature decreases with altitude, as it gets higher and higher, it gets colder and colder, meteorologists can estimate how tall these clouds are. And just looking at this, we can make some kind of broad assumptions. These clouds are higher than these clouds because they are brighter. The nice thing about infrared is it shows water vapor in the air as well as the height, movement, and speed of this water vapor. So even if it hasn't formed a cloud, it usually will show up. So it gives us a little bit better picture all the time. The next kind of tool we use is these radio sondes. And these guys measure temperature, pressure, and humidity of air at different altitudes. What happens is here, where this guy's holding, there's an instrument package attached to this balloon. As it is carried into the atmosphere, it transmits information back to the ground while computers track the balloon's position. This helps us determine the stability of the air, the likelihood of thunderstorm formation, and by piecing together information from several of these, we can see how air is traveling in a certain area. These ones, the downsides to these ones, of course, is you have to have a whole bunch of these going up. You have to have a whole bunch of people, giving data and sharing it back and forth. So they're not as good as the satellites as far as like ease of access, but they do give more descript local kind of conditions going on. The next kind of tool we use is just surface observations. This is kind of just what's happening at weather stations right there at that moment. So we have a lot of these surface kind of weather stations at airports. We have commercial jets have a lot of weather equipment on them. We put them on buoys. We have them on ships. These weather stations can be just about anywhere. And these report the weather each hour, or they can be programmed to, in dangerous conditions, give the weather more often so we can have a better picture, a better like real-time thing of what's going on in that local area. These surface observations usually include temperature, dew point, barometric pressure, wind speed, and the direction of the wind, the visibility at the site, cloud height, and cloud cover. So that's a lot of information. How do we graphically take that information and put it into something? What we'll use is called a station model. And station models are a condensed method of conveying information from weather stations. And the nice thing about station models is they're universal, so anywhere you go in the world, you should be able to read these. This is a station model right here. This picture is a station model. It's got the wind, the temperature, the weather, the dew point, the sky cover, the pressure, and the sea level pressure. And everything on here is significant. The direction of the wind here is significant. These little flags tell you how fast it's going. And the symbols that we use on these are over here. So like, for example, this one has a open circle. That means that is a clear sky there. It has this little flag here with one little one and one big one. That means that the wind is going at 15 knots and is going in the northwestern position here because it's pointing in that direction. This weather here, we got this ... We got heavy rain happening here. We got the temperature going on there, the dew point. So there's lots of really, really good things on there. And then we've got surface maps. So every 3 hours, the National Center for Environmental Prediction, or NCEP, makes an official U.S. weather map. It looks like this. This organization is based all the way over here in Maryland. Using station models from a lot of local weather areas, this computer makes this map. It makes these isobars, which are these ones here that all the same pressure. It identifies the high areas, it identifies the low areas, and then forecasters can draw in the fronts and see how these guys are moving through these weather systems. So we get a new one every 3 hours, so we can see what the new kind of weather is going on there. You can see that there's troughs on here that we've talked about. There's these cold fronts, occluded fronts, warm fronts, all of the things that we've kind of been piecing together. There's a stationary front here. So very, very cool. The colors indicate the weather type. So rain is kind of this green. Mix of snow and rain is this purple. Snow is just blue. So these are very cool. One of the things that we really care about with weather is forecasting. So usually nowadays these are all computer generated. It used to be you'd have a lot of meteorologists looking at this data and kind of trying to interpret it. But now meteorologists are more trained to interpret these computer models and kind of see what's happening there. So we take current weather data, we use mathematical equations, and we see what is going to happen to the atmosphere. In this thing here, you can see that this rain is moving kind of from west to east. As this weather condition continues to change, the model continues to change. So that's why the weather in the morning is often very different than the weather in the evening. As we get more urbanization in areas, we get climate, as we get kind of changes, as we get more concrete, observing more heat than in natural areas. But we use these computer models, and then we still use local weather patterns, things like your farmer's almanacs, to see what happened last year and kind of base that weather off of what's going to happen this year. If it was a colder winter, then it's probably going to be a colder spring. So we can kind of do these regional trends. This is the conclusion of chapter 20. This is a long one, but I hope that you learned a lot in here. I hope you learned about air masses and fronts and how these air masses form and how these fronts move. We talked about thunderstorms and severe wind in the form of tornadoes and hurricanes. We talked about winter storms, and we talked about station models and forecasting. So this has been a really kind of action-packed chapter. If you have any questions, let me know, and we'll see you in the next one.